Today we are up against an absolute beast of an integral. It's the integral of the 6th root of tan x dx. So I've done the 4th root of tan x on this channel, and as for cube root and square root, well, those are pretty common on YouTube. Probably go to Black Pen Red Pen's video on those. But yeah, okay, so how do we do this? Well, firstly, I'm going to define some useful functions just for clarity, okay? These aren't anything crazy, it's just because they come up a lot in this integral. So we'll define the t function as this thing. It takes in two inputs, by the way. And we'll define the L function as this other integral sort of thing. It's the integral of 1 on u squared minus a. These come up way too much in this integral, so I'm just going to define them here so I can use them. Also, a is positive for these two functions. So how do we integrate this? The first step is basically substituting the entire integrand. That will give us a sort of rational function. So we define t as this thing here, 6 root tan x. Then, well, this will become t. And dx is just this thing here, which I just calculated. I left the details out for you, but you can check it yourself. Right, so how do we go about this part? Well, we can write this as a sum of cubes. And we can just use the sum of cubes formula. And this way we're kind of factorizing the denominator in a certain way, which is probably what you want to do for rational functions, at least in this case, and in a lot of cases actually. Okay, so how do we do this? Well, we can cancel the t to the 4 plus 1 with t to the 6 if we write it in this way, and yeah, that's fine. And now we split up the integral into two parts, and those t to the 4 plus 1s will cancel. As for this second integral, the denominator is still the same as before. We can just replace it with t to the 12 plus 1. Okay, now we have two integrals. I'll define I1 as this first one, and I2 as the second one. Let's do I2 first, because it's a bit easier. So how do we do this? Well, we want something with t cubed, because then we can just substitute z equal to t cubed. And well, we want a 3t squared to complete it. So I mean, we could just do something like this. Now the 3t squared dt will transform into dz. And in the end, we're just left with z to the 4, or 1 plus z to the 4 in the denominator. This is a pretty classic kind of integral, pretty similar to square root tan x integral. You just divide by z squared, top and bottom, and then do some nice manipulations, which will become clear as to why I'm doing them after I do them. So first I'll do this, and plus 1 minus 1, maybe factor this a bit, and split up into two integrals. Okay, now the bottom you can actually factorize as z minus 1 on z squared plus 2. And the other one, well, you can also factorize in a different way. Z plus 1 on z squared minus 2. You can check those for yourself. So if we let w equal to this, then in this first integral we get w squared plus 2 here, and then dw, because that's just how it works. If we let chi, which is this Greek symbol, equal to z plus 1 on z for the second integral, we get something similar, and you will recognize these two integrals as basically the t and L functions. So normally this would just be 1 on root 2 inverse tan w on root 2, but I don't want to have to keep writing all this stuff, so I'm just going to use the t function, t of, well, this constant here, which is 2, and then w. W was just z minus 1 on z. And this would be, well, the L function of 2, and then this chi, which is z plus 1 on z. Okay, now we're done with I2, let's do I1. So I1 is a bit, well, actually quite a lot more difficult. We can factorize this denominator in a pretty cool way, using a completing the square sort of trick. T to the 8 plus 1, you can write as t to the 4 plus 1 squared, minus 2t to the 4, I think. And then, yeah, of course, we have the minus t to the 4. If you expand the right-hand side, you're just going to get this thing here, minus 2t to the 4 minus t to the 4. And these will just cancel out, right? Yeah, so you're just left with that thing on the left-hand side. So these are equal. Now, well, we can just do a difference of two squares and combine it into one factorization. So there we go, we factorized the denominator. We're well on the way. So I'm just going to apply this here, and now we have a sort of partial fraction sort of thing going on. If you consider the integrand, but replace t squared with v, just to maybe simplify things, you can kind of see this will be a pretty good partial fractions. You could just find the coefficients by solving for them, like let them be a and b and solve. That's kind of annoying though. There's a pretty cool way to do this. consider the difference of the two factors in the denominator. So that factor minus the other one, you'll see everything cancels out except the v term, which would become a 2 root 3v, right? Yeah, 2 root 3 times v. So that tells you that the difference of the factors in the denominator is basically similar to the numerator. So if we just put a 2 root 3 here and a 2 root 3 here, now we can write the numerator, which is 2 root 3 t squared, as the difference of these two things. Okay, well now you just split up the fraction and you'll see stuff cancels on each individual fraction. And when we have two integrals, okay, now to solve these, you just divide by t squared on each integral. That would give you something like this. And now we want to use some nice factorization. So these are the factorizations we use. You saw them earlier in the video. So t squared plus 1 on t squared. Well, we need to introduce the derivatives of those. Yeah, okay, so basically you do something like this. I won't go through all the details. But now we can split this up into 4 integrals. So if you split the first one up, well, you get that integral minus that integral. If you split the second one up, you get this minus that. Okay, should be fine. Now we just have to deal with this. So t squared plus 1 on t squared, well, we can factorize that using, I think the second factorization is better. So if you use this one, t minus 1 on t all squared plus 2, then the derivative of t minus 1 on t is on the numerator, so that's pretty good. Great, now on the second one, we'd use this other factorization. The derivative of t plus 1 on t is on the numerator now. And, okay, we can use the t minus 1 on t factorization here. Wow, this is really a very painful video. Okay, so we have this plus that, and then t squared plus 1 on t squared. Well, that would probably use the t plus 1 on t. Okay, yeah. Great. So now everything's in the perfect form. This is just a reverse chain rule form of the t and L integral formulas that I had at the start. Also, I probably should simplify this constant factor. It's just going to be root 3 on 2. So let me just repeat that across all of them. Okay, done. Now let's convert these into the t and L integrals. So this would be t of 2 minus root 3 and then t minus 1 on t. Yeah, okay, seems fine. Now this other one is an L integral because it's 1 on something squared minus 1 on u squared minus a positive constant, basically, if you do a substitution. Okay, hopefully you understand that. I don't know, this video is really cooked, so I don't know if I'm explaining this well. Anyway, so this next one is a t integral, and this last one would be an L integral. So 2 minus root 3 is the constant. T plus 1 on t is the actual thing. Okay, now we're done with I1 and I2, and if you combine them all together, you get this as our final answer. To convince you, I'm going to put this in Desmos. So in Desmos, we'll define the t functions as we did at the start. And, well, the L function was basically this thing. Okay, cool. Now, t, or lowercase t at least, is equal to tan x to the 1 on 6. That's the first substitution we did. And z is equal to this t cubed, right? So tan x to the half. Right, so now we want to write our answer as a function. I'll call it capital A of x. But anyway, this is what our answer should be. And now we just differentiate our answer, and we should get back the original integrand, because that's how integration works. And does it? Okay, yes, it works. What a relief. Okay, it does work. So basically, the green graph is the integrand. The red graph is the derivative of our answer, and as you see, they do match. Don't worry about the lines going off, that's just Desmos bugging. But the graphs match, so our answer is correct. And if you want the full answer in terms of only x, no other functions, no nothing, this is it. Wow. I'm actually shocked that I could do this. This was a huge pain to go through. Thanks for watching. I'll see you next time.